All right, our next team is Team 5 with the curious name, Securiosity Killed the Cat.
Hi everyone, I'm Adam McLaughlin, this is Paul Carpenter, and this is Jeff Sternberg, and we are Securiosity Killed the Cat, and our project is the video condenser. So security cameras have become ubiquitous in society as of recent years. There's over 4 million cameras in Britain alone, and big cities in America are often using security cameras at traffic locations for ticketing purposes. And unfortunately, these cameras run 24/7, and inspecting the videos that they produce is a manual process. Someone has to sit there and actually watch these videos and try and find any significant moments that occur. So what we propose here is video compensation. It summarizes these videos without losing events. But unfortunately, the original algorithm given to us for video compensation is kind of slow. So our project was to put this algorithm on a GPU to speed up as fast as possible. Video compensation is pretty novel in the way that it can take a video and remove any inactive elements by preserving any dynamic content that the video may have originally had without loss, so we don't lose any information. And basically, we're trying to prevent this. Okay, so our customers, which is Professor Conrad and Professor Ishwar, they want real-time realization of this process, and the key of this, as Adam said, is implementation on a GPU, which has hundreds of cores, whereas the CPU, which is what the original algorithm ran on, only has multiple cores. The card that we use is an NVIDIA GTX 480, which has 480 processor cores to handle the process. By implementing it on this GPU, we get to use CUDA, which is NVIDIA's parallel programming architecture, and this leads to parallelization and speeding up. The video condensation process is carried out in 2 major stages: background subtraction and video condensation. Background subtraction is what identifies moving and non-moving pixels, which represent moving and non-moving objects. And then video condensation removes these objects that don't move. A few engineering requirements. Obviously, parallel processing must be used either on CPU or GPU. GPU is the obvious choice. 30 frames per second must be condensed, which represents full motion video. At least one type of camera must interface with the system, which is the Axis pan-tilt zoom cameras that are mounted on the building. And target resolution of video is 320 by 240 pixels.
So background subtraction is the process that we use to distinguish movement pixels. The particular flavor of background subtraction we are using, we implemented 2 versions. The regular go background subtraction using a threshold scaling based on deviation from incoming pixel data, and background subtraction using the Markov nearest neighbor technique. To do this, we start with baseline, which is typically 100 frames. You want to use a small number so you don't have a lot of overflow coming in later. The incoming pixels compared with each incoming pixel is compared with this corresponding pixel in both backgrounds. If the pixel exceeds both set thresholds, then the pixel is considered moving. And the background's updated based on this new data. This is the Markov nearest neighbor comparison. Using single pixels causes a lot of noise. You'll see flicker and individual pixels just lighting up as the video goes on. So we use a checkerboard. We use a checkerboard pattern. And we start with the O's. We take the white, all of the surrounding values in the white pixels, sum it in location on the O's, and we use that number to factor the threshold. We then do the same thing for the X map. We take the black squares and put the sum in the surrounding areas. And we continue to alternate back and forth between the 2 for some iteration count. We don't wait for convergence, we just continue after we've done a certain number of these iterations. We got really good results using the GPU with background subtraction. We created a serial test code with to test the Markov. We got a time of 2,600 seconds. Our GPU code with the same identical algorithm implemented ran in 120 seconds. There were some other overhead times associated with these. OpenCV, which was our image processing library, had a 35-second I/O time. The test video we were using for this was uncompressed in the size of 2.7 gigabytes, and that went back and forth once. There was some overhead associated with setting up and running code on the GPU for memory transfers and other time for instantiation. We measured that overhead to be 30 seconds. So for straight processing time, the GPU algorithm took 55 seconds, and the CPU algorithm took about 2,550 seconds. These times are variable when we tested, which is why there's an approximation.
Okay, now it comes to the condensation, which is the actual removal of the non-moving pixel data that we determined from the background subtraction. So it actually takes a novel idea for image seam carving that was originally produced a few years ago in 2D, and it extends it to 3D. And the 3D seams are actually ribbons, as you can see in the middle pictures here. So we have a 3D box, and that has coordinates of x, y, and t in our coordinate system, which represent the horizontal pixels, the vertical pixels, and the frames coming in. And then we can project that onto a two-dimensional domain for a vertical ribbon on y and t, and then a horizontal ribbon with x and t. And the algorithm works by finding these moving pixels from the non-moving pixels with the background subtraction that Jeff just talked about, and then using this algorithm to find the ribbon, but that passes through only static pixels to remove as much content as possible. We remove the video, and that shortens the video by 1 frame, and we repeat the process as much as possible. Ribbons can actually flex to varying degrees. So on the top 3 pictures here, you can see we have a flex of 0, which means the ribbon can only either remove a frame or not do anything at all. In the middle pictures, the ribbon's allowed to flex a little bit, and such that it can actually go between frames, and what this actually produces is the actual ribbon carving, in which different frames can be merged together in our output video. And then for flex equals 2, it allows even more flexibility and more change in time for one ribbon itself. The algorithm has a certain flow to it. We start with our input video, and we pass that through the background subtraction to get our cost video, which is just a binary video telling us whether or not something is moving or not. A white pixel being something moving, a black pixel being something that's part of the background. We feed both these videos, the input and the background subtraction cost, into our flex equals 0 algorithm, which again just either directly removes a frame or keeps it, depending on our stopping criteria. The flex equals 0 algorithm produces a flex equals 0 video and a flex equals 0 cost, which feeds into our flex 1 algorithm and does the same thing until we get our flex 2 output from the same process. So we end up with a whole bunch of output videos, so you can see how the video condenses along the way. Our parallelization here was able to decrease the amount of time needed for the algorithm, but unfortunately our results weren't as good as we expected, and they weren't as good as the original background subtraction results. You can see that flex equals 0 here runs in real time, as it took 159 seconds to execute on our GPU, but and the original video was actually 169 seconds. Unfortunately, the whole algorithm itself would consist of the background subtraction, flex equals 0, flex equals 1, and flex equals 2. So in order for the entire system to run in real time, we would need all of those videos to be processed in real time. Flex 1 and flex 2 code are actually the exact same algorithm, except for the change of the variable for flex itself. So it only included the flex 1 code here in this table. So the big question is, why couldn't we achieve real time for the video compensation? Well, GPUs are designed to compute a lot of floating point operations per second, or flops. And they're mostly designed for applications like video games, where you're constantly computing pixel values and things like that. And the background subtraction algorithm is perfectly designed for that. We do a ton of floating point operations, and it's highly parallelizable. Now, if we look at video condensation, we actually are doing a lot of memory shifting. So we're taking some elements, we're pushing them forward, or we're pushing them backward, depending on how the ribbon bends. And while CUDA code can parallelize this process and make it faster, it's not designed to actually just do memory. Memory is a key point of high performance computing, and if you can't handle your memory properly, then other optimizations become way less significant. And that's our bottleneck here. It's actually memory. So the algorithm itself deals with memory a lot more than it actually does with actual computation, and that's why it's simple to optimize.
Okay, so moving on to a slightly different aspect of the project than the rest of my team. The video condensation project originally had somewhat of like the hardware aspect planned for it, which was interfaced with the Axis camera, but as we went on, we eventually found out that this was simply calling the IP address of the camera to make it work. So we decided to come up with a hardware task that called for switching between inputs of 4 different composite video cameras. And this allowed our group to kind of explore PCB design stay within the realm of video processing and work with composite video source, which is low bandwidth and pretty easy to handle. So here's the overall system diagram. As you can see on the left, you have the 4 video sources, which go into the 808174 analog mux. And then it passes on to the 808055 buffer, which amplifies the signal by 2, since high convention composite video, it varies by about 6 decibels, so that translates to about a 2-to-1 gain. And then it goes to the output, and then from the output you can either put on like a monitor or TV. The mux is controlled by digital inputs, controlled by a switch on the board, which is powered by 5 volts. So a closer look at that. There's a truth table at the bottom. So there's basically 3 switches. First to control which camera you select. So 0, 0 corresponds to input 1, 1, 0, the next one, and so forth. Then shutdown switch just shuts everything off completely. Here's a look at the final product. So you see the 4 input sources on the left and the output on the right, and the switch in the middle. And here's the budget estimate for the whole project, since again it was mostly software based, and the hardware was pretty much an afterthought at the end. The only 2 things that we had to take care of was the actual video card itself, the 480, which was $40–70, and then the power booster, since the computer we already had needed an external power source to supply the card. Questions?
How do you guys manage camera jitter?
One of the cameras that we use has its own jitter adjustment already. So it's supposed to be a 30 frame per second stream, but you'll typically see it displaying at 26 or 27 when it's cutting. Jitter will mess with our motion estimation.
Oh, signal and ice, so you have pencil themselves, what does that do with the environmental current?
So you actually can. You don't want to move the camera. But if you do, our background subtraction will adjust within 5 to 10 seconds. In tests of our video, you'll see someone who will stop at a crosswalk or something who's crossing the street. They'll stop for 5 seconds and they'll disappear. And they'll become part of the background. And then magically they'll appear out of the black and start walking across the street.
The PC board, that's something that you designed, and if so, how many layers did it have?
2 layers.
You designed that.
Yeah.
If you were to, your background suppression was faster than real time. If you were to, resolution was fairly low than we're dealing with 2040.
Yes.
What if you wanted to run this on a camera?
We would have to reorganize the kernels a bit, right? So the way in which we design our kernel, and this is getting kind of technical, is based on one of the dimensions of the video. So we would have, for an HD camera, we'd probably have to rewrite our kernel.
For an HD camera, we would.
But for a 640 by 480, we'd be able to use the same code.
We handle under 640 by 480. The limiting factor is the height.
Microfilm calculation, would you be able to attain time with, say, 1920 1080?
So
Yeah. I think our Markov implementation handles 80 to 100 frames a second. 1920 by 1080. That would increase the size of the video. 6. To increase it, we squared 27 times. Have to check.
they got the straight controls, yeah.
The speed up that you were able to get, how sensitive is that to the type of graphics card that you chose? And is that one a high-end card, or can you say something about that in terms of the number of cores, the sensitivity? respect to that?
Yeah, our results are definitely affected by the flavor of graphic card we're using. We're using, at this point, it was top end when we got it, it's now medium end. There was an update in hardware while we were doing the project. This is, the speed of the board is the same as the research, NVIDIA's research boards known as the Teslas. So the only difference between our card and say a higher end card would be the amount of RAM available. Lower end cards we would not see as much speed up. It depends on the specifications. And also the thread count. Some of the lower end cards are either lacking in available threads or they have a very small number of threads or just not as many of the current card that we're using.
So after this project wasn't a great success in terms of the implementation, what do you think of? Would it be any better running on, let's say, CPU with recent AMD 12 core? Would there be benefits, or basically the whole algorithm is such that it's not really parallelizable anyway?
I think I'd go with the latter because the video connotation again had like those memory issues. So no matter how many cores you're gonna throw at it, it's only gonna help so much.
I don't know exactly about that. You do pre-processing, you could. If you split up the video chunks, since there's sort of there's a region of it, there's a region of interest. If you depending on what your dependencies are from previous stages, you could the CPUs are gonna if you leave the same if you do multiple chunks at a time, you're gonna get a lot of memory coherence. Memory repeats, in which you're going to get the biggest benefit. So if you could do it in parallel, not multi-core but multi-processor, it would be possible to see some speed up. The timing that we showed, the 1300, that's actually an optimized time. In unoptimized code, we saw timings of 1800 seconds. It was a 500-second increase. You'd have to heavily partition the work.
I know GPUs have higher error rates than traditional CPUs. Did you do anything to take into account of that, extra error checking in your software, anything like that?
In our experience, we haven't been able to find deviation between a GPU calculation and a CPU calculation.